our lecture. What we're going to do next week is just going to be revision class, which I also encourage every one of you to also attend, because I'm actually going to be discussing, something that is very crucial to the final from Monday. But we're going to finish the last topic, which is a logistic regression, this week, Friday. I also want to announce to you that the final practice questions have already been uploaded. You can check the course module. I uploaded that without solution. And of course, I'm going to upload the solution on Friday, okay, to the final practice questions. Of course, the final practice question will actually revolve around 3 areas. Like I said, the principal component analysis, repeated measure ANOVA, and the topic we're doing now, logistic regression model. And of course, today, I'm actually going to release a rubric for practical 3. Of course, the practical 3 was due, I think, last night or this night. So, but I'm actually going to release the rubric for practical 3. Okay, so once again, I want to welcome you to another exciting. Oh, before I go into the topic, I extended the submission of the ongoing assignment by 24 hours. So it's going to be due today, because the essence of the extension is because of the fact that I was not able to make it to my office hour last week, and maybe somebody still needs some clarification. Then there's something I'm also quickly want to discuss in the assignment. I know you're going to get to a point where you actually going to have a degree of freedom of 0. And the question now is, if I'm comparing modules and I have a degree of freedom of 0, what is going on? Where there's no way to, figure out what the p-value is. And if there's no way to figure out what the p-value is, it may be difficult for you to take a decision. Let me tell you, that kind of situation is also going to be part of what we want to discuss today in assessing logistic regression model, that we actually call saturated model. Now, in saturated model, the degree of freedom is actually 0, because of the fact that the numbers of parameters in the model is the same as the numbers of observation. I'm going to say that again. When the numbers of parameters in the model is the same as the numbers of observation, at times we could lead to that problem. Now, situation where the degree of freedom is 0, and I'm comparing a simpler model with a complicated model, always declare for the complicated model. I'm going to say this again. Anytime you are comparing 8 or 2 modules, and you find out that the degree of freedom equal to 0, because the degree of freedom equal to 0, you may not be able to obtain the p-value. Then you conclude in favor of the complicated. Conclude in favor of the model you have in the alternative. Does that make sense to everyone now? So whichever models you're comparing, if the degree of freedom equal to 0, where you are not able to get your p-value, your conclusion should be in favor of the complicated model. Should be in favor of model in the alternative. Okay. I want to welcome you to another exciting statistical topic. Of course, the topic today is assessing logistic regression. In the outline, I'm actually going to talk about investigating model absorption, then walk you through illustrative examples. Now, let me tell you this. Every statistical model has assumptions. I'm going to say that again. Every statistical model, including logistic regression model, has assumptions. And let me tell you this, the assumptions will revolve around the stochastic components in the model that I call the random components, that I also call residual, that I also call the place of unexplained variation. Now, looking at the logistic regression model, we have a lot of assumptions. Number one, do you know we expect to have a linear relationship between the logits of the response and the explanatory variable? I'm going to say that again. There should be linear relationship between the logits of the response and the explanatory variable. You know, I did not say linear relationship between the response. I said the linear relationship between the logits of the response and the explanatory variable. Of course, we know the relationship between the response and the explanatory variable cannot be linear, but the relationship between the logit of the response, what do I mean by the logit of the response? I'm actually talking about the log of odd, log of odd. The relationship between that and the explanatory variable has to be linear. Okay, before you can trust your logistic regression model, you need to investigate that. Another assumption that we're going to talk about is the way the sample is collected, because we expect to have assumptions of independence of observations. Observations should be independent of one another. But do you know how you can actually attain that? When you use the principle of randomization, when you are taking your sample, you're taking your sample randomly. When you're taking your sample randomly, independent of observation can be guaranteed. We have another assumption. When we have when we have what is that? Okay, maybe in the other class, right? Or my phone. That should be in the other class. Okay, now, but that is not disturbing you, right? Okay, maybe they are having a session. Okay, now this is what happened. Actually, what I'm trying to talk about is situation where you got a lot of explanatory variables. We also, there should be assumptions of absence of multicollinearity. The same way you investigate multicollinearity in multiple linear regression, you're also going to do that here, where you're going to get your VIF. You get a VIF of the explanatory variable, and of course, you use a threshold of 5. Anyone that is greater than 5, of course, there's a problem, right? You can investigate that. And there's also, we also expect the absence of outlier. There shouldn't be outlier. And another assumption is that the response variable should be categorical. It is required. The response variable should be categorical. Of course, there's nothing like normality assumption. Okay, there's nothing like normality assumption, because the underlying probability distribution of the response is Bernoulli. It's not normal. So we don't require normality. Does that make sense? Okay, now when you're assessing a model fitness, just like what we do in the linear regression, where we conduct a statistical test on the individual parameter in a model, we make use of a t-test. But in the case of logistic regression, if I basically want to test whether the log odd estimate of the slope, I told you the other time, we don't call it estimate. Okay, the output, the estimate that came from logistic regression are called log odd estimate. If I want to test whether the log odd estimate equal to 0 or not, okay, if I'm actually conducting a significant test, I'm actually going to use conduct a word test called z-test, which is still going to be the ratio of the log odd estimate to the standard error of that. And I can actually obtain the p-value associated with that, putting into consideration the distribution of the z is normal, with mean 0 and variance 1. Of course, I can take my decision, I can get my p-value with that. Okay, now let me tell you this. We find ourselves in a world where we basically want to compare two models. I want you to look at model 1. Model 1 is a model without covariate, or a model without explanatory variable. If you take a look at that, I'm only we're talking about intercept model. When you're considering intercept model, it's more or less like you're only focusing on the mean of the response. You are not interested, there's no connection between the response and any explanatory variable. That's what we call intercept model. We also call that a model without covariate, or a model without predictor, or a model without any explanatory variable. Okay, so which means whether satellite is present or not does not depend on any factor. Now, when you take a look at the second model, the second model is actually saying that the satellite present depends on the weight. The weight here is an explanatory variable. If you take a look at these two models now, is that you are comparing a simpler model with a complicated model. The simpler model is a logistic regression model here without any explanatory variable. I'm actually going to call an intercept model. Comparing with a complicated model, where the response variable is related to the weight. Okay. Now, when you take a look at that, you take a look at the p-value associated with that. Of course, the non-hypothesis is going to support model 1. Alternative is going to support model 2. And you're always going to compare your p-value with a standard level of significance. When p-value is less than standard level of significance, of course, you're going to reject the non-hypothesis. Rejecting the non-hypothesis, you're actually telling the world, there's a connection, there's a relationship, there's an association, there's a linkage between satellite being present and the weight. That's exactly what we mean. And of course, here we're using the likelihood ratio test. This is not going to be the first time we're using the likelihood ratio test. Okay, we've used that before. But there's something I need to pay attention to. When you are using the nested ANOVA here, you need to specify that the test you are using is chi-square. Look at the difference. Otherwise, if you don't specify chi-squared, it's basically going to give you the one on the nested ANOVA test, and that is going to be wrong. I advise when you write ANOVA, when you are comparing two models that are nested in logistic regression, you need to specify test equal to chi-squared. The distribution, the probability distribution, when the non-hypothesis is true, follow chi-square distribution. And that's why you need to actually put a chi-square, test equal to chi-square. So I need you to take note of that. Now, when you talk about intercept model, another name for that is what we call norm model. Okay, norm model. Now, I quickly want to say this. When you are trying to look at the compatibility between observed data and they fitted. What I mean by fitted, the one you predict from your model. Okay, we basically want to see whether there's an agreement between that. When we want to do that, we're going to talk because the model that fits the observed exactly. I'm going to say this again. A model that fits observed exactly. I mean, the observed data exactly is a saturated model. What do I mean by saturated model? In a saturated model, every observation we have their own separate parameter. If you have 100 observations, imagine that it is expected that you have 100 parameters. In that kind of situation, you know what happens to the degree of freedom? The degree of freedom will be 0. Okay, but that is the exact model. I told you, we find ourselves in a world. We can never have an exact model. Our model can never capture exact reality. I remember when George Box was asked about how true a model is. George Box replied, if you mean a whole truth, our model is not true. When you mean a whole truth, our model is not true. Because there's always going to be a place of error. Our model cannot capture reality. You get what I mean? Because of that, okay, the saturated model is highly complicated. It is not the one that we expect in a real life practical situation. It's like going into an extreme. When I go into an extreme, I have a saturated model to the right. When I go into an extreme to the left, oh my God, what do I have to the left? I have an intercept model. The intercept model is when I have just one parameter. What is the only parameter in the intercept model? For the intercept. What is the other extreme? Saturated, where I got a lot of parameters in my model. What would be the ideal model? What would be the one that we expect in real life, practical situation, would be the one that come in the middle. The middle of what? The middle of the non-model and the saturated model. Now, do you now understand what we mean by saturated model? The saturated model is like going to the extreme right, where you are assuming parameter for each of the observation that will look too complicated. That can never happen in this part of the world. Don't let me say part of the world, in this world, in a stochastic world, where we live in a probabilistic space. There's always going to, because there's more than one state of nature. When there's more than one state of nature, oh my God, there's always going to be an error. We don't expect a saturated model. And that is why the degree of freedom for saturated model will be 0. But the ideal model we're looking for is the one that falls in between of a null model that I call an intercept model and the saturated model. Take a look at this. You're going to see the clear picture now. Look at the 3 models. Saturated, what is the log likelihood? 0. Deviance, 0. Numbers of parameters is 173. That 173 is the same as the number of observations. That is too complicated. The norm model is an intercept model where we only have one parameter. What was the parameter here? Beta naught. The current model is the one that we come in between now. How many parameters do we have? We got 2. Beta naught and the beta 1. Why are we having 2 parameters? Beta naught, beta 1. The beta naught is for the intercept, the beta 1 is for the width. Don't forget, we're looking at the effect of width on whether the satellite is present or not. Okay, so take a look at that. We have, so the current model now is an ideal model, which is the one that comes in between the non and the saturated complicated model. Okay, of course, in logistic regression, we normally want to consider, we use a likelihood ratio test to decide between the intercept model and the complicated model. Okay. And of course, don't forget, we normally use a Watt test, like I said, and the distribution is chi-squared. And of course, we make use of the AIC. The AIC is just talking about 2 times log of the likelihood plus 2 times P, where P is going to be the numbers of parameters in the model. Okay, the model with the smallest AIC is the best model, but AIC will be meaningless if you are only focusing on one model. Like, is it possible I'm comparing myself with myself? So the AIC is going to be a good module selection criteria when you have at least 2 modules and you're going to go with the one with the lowest AIC. Okay, so that was why I said the AIC is only meaningful in comparison to another module. By itself, it is meaningless. Okay, by itself, it's meaningless. That's exactly what I mean. Okay, now let me tell you this. We don't expect, when we actually dealing with a classification problem, okay, where the response variable is categorical, how do we actually investigate whether our model that we have chosen is really doing great? We actually need to compute what I call a confusion matrix. The confusion matrix will enable you to know, the probability of misclassification. Let me tell you this. We can never have a perfect model. We don't expect, to have, perfect classification. There's always going to be errors. But what we're actually trying to do is to minimize the error due to misclassification. And how are we going to do that? What we're going to do, and that's why in statistical analysis, even in machine learning algorithm, we normally split our data set into 2. We're going to have a training set. We're going to have a test set. A good number of the data set will be committed to training, maybe about 70 to 80 of the data set committed to training. And the other one will be committed to testing. Okay. Now I'm actually going to build my model based on the training data. Then I'm going to evaluate my model using the testing data. So what am I going to do? What I'm basically going to do is I already know the true status of some particular response variable. I want my model to predict that, but I want to tell you our model can never predict correctly. We already appreciate the fact. Now, take a look at what I'm trying to show on the board. Predict.satellite. I want to use them. We've chosen model 1, right? If you choose a particular model and you write a type equal that response, and with the data you're using, of course, we're going to have some predicted values, right? And we're also going to have original observed values, right? We're going to place a threshold greater than 0.5. Why do I go for greater than 0.5? Okay, 0.5 is is using chance, right? But more than 0.5 is basically what we want. If you take a look at what I'm showing you now, that look like a matrix. 0 and 1 is what happened in reality. Okay, false and true is what your model predicts. I think I'm gonna write something on the board now for you to see. Give me 1 second. Okay, now what I'm going to write on the board, I'm going to write actual, predicted. Okay, actual, predicted. Now, in the states here, in the actual 0, 1. Okay. Now, when I have 0, 1, then I'm going to have true here, and I'm going to have false. Now, take a look at that. This is what happened in reality. This is what our model predicts. Now, look at this. True positive. Now, right here, I'm actually going to have true negative. In the diagonal, that's a correct decision. Okay? But if you take a look at false positive, false negative, in the left diagonal, that's a wrong decision. Okay? Now, if you take a look at what I have now, we got some metric. Now, if you compare that with what you have on the board, that we have 27. Oh, give me 1 second. I think I'm going to put a false here to go by what you have there. I'm going to put it through here. Okay, so you have 27, 16, 27, 16, and you have 35. Okay, and you actually have 95. Okay, now what does that mean? Okay, when you is 0 and false, they go together. Okay, 1 and true, they also go together. If this one is trying to say, you know, when you have a true positive here, it's just trying to say that there's an agreement between the state of nature and what your model predicts. Now, when you take a look at this guy, okay, there's an agreement between the state of nature and what your model actually predicts. Now, when you take a look at the total here, okay, the total here is TP plus FN. Now, let's take a look at this. True positive, false negative. These are the total number of positive that we have, right? True positive. For, you know, when I say false negative, they are not necessarily negative. They are positive, but the model classify them to be negative. So this is going to the everything that you see here is the total number of positive that we got. Now let us also look at this. False positive, true negative. Okay, false positive, true negative. That would be the total number of negative that we have. This is the total number of negative. False positive is a negative. It's not supposed, you know, it's not supposed to be positive, and the model classify that as positive. That's why it's called it false positive plus the true negative. So this is the total number of negative, the total number of positive. Now we're going to have 4 different measures. Measure number 1 is what we call sensitivity. Okay, the sensitivity now, if you're talking about sensitivity, that is the ability of your model, okay, to dictate an effect when it is present. Maybe you have a COVID equipment, the ability of a COVID equipment to detect COVID when COVID is present. That's what we mean. Now, the sensitivity, another name for sensitivity is true positive rate. You know, true positive rate. True positive rate. That's another name for. We also call it recall. That's another name for it. Recall. Recall, true positive rate or sensitivity. And that is going to be true positive. That will be defined as true positive divided by all positive, divided by this guy plus that guy. You see that? So this guy here is the sensitivity, which is the ratio of true positive to all positive. What do I mean by that? You know, the model was able to correctly identify, you know, positive, you know, the positive. The model was able to correctly identify positive. That's what we mean by the sensitivity. That's what we mean by true positive rate. So if I want to find the true positive rate now, okay, I'm actually finding the sensitivity. Okay. Now, another thing that I want to talk about the false negative rate. False negative rate. Let me see. I think you all see this, right? Now, in the false negative rate, okay, I'm still going, the denominator is still going to be all positive. The denominator is still going to be all positive. So false negative rate. The false negative rate just talking about, when the numbers of positive were incorrectly identified. The proportion of that, it tells you the positive class got incorrect or classified. They got incorrect. So which is going to be Fn, okay, divided by Fn, okay, plus Tp. Now take a look at this. False negative divided by, true positive here, false negative, all of this is a total number of positive, the denominator. False negative and true positive is total number of positive. The Fn is false negative. Okay, so the false negative rate this is it. Okay, so which actually tells us the proportion of the positive class, that got incorrectly classified by the classifier. Now, the next thing I'm also going to talk about is specificity. 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 Is the ability of the model, for instance, in the case of disease is not there and the model dictates absence when the disease is not there. Of course, we expect the model to detect absence of the disease because the disease is not there. Okay, which means we expect the model, not to detect anything, any effect when the effect is not there. And that's exactly what we mean. So by specificity. So it's actually, and another name for that is true negative rate. We call that true negative rate. That's what we mean by true negative rate, which is Tn over Tn plus Fp. What do you have here? The denominator is all the total of negative. Why? True negative plus false positive. False positive supposed to be negative. Does that make sense? That's why the denominator here is negative. Okay, this is what we call specificity. Okay, now it's actually tell us the proportion of the negative class that got correctly classified. Proportion of negative class that got correctly classified. Now, what about the proportion of negative class that got incorrectly classified? That will be false positive rate. False positive rate. Okay, the proportion of a negative class that got incorrectly classified. This one is true NR, and this is FPR. Okay, when you take the acronym, so which is FP divided by TN plus FP. Okay, so take a look at that. And do you know that this guy is also 1 minus specificity? It's also 1 minus, because if you add this to this, it will give you 1. And that's why this guy is 1 minus that guy. So please know the relationship. Now, based on the data that we have, how can we get all of that based on this now? Okay, I'm actually going to show you. We actually have several metrics of evaluation. I just to show you sensitivity, specificity, and so on like that. You've got a lot of metric of evaluation, but there's one that is highly important that we call AUC. Well, the AUC is more or less we're talking about the area under the curve of receiver operating or curve. And what we do there is we actually have a plot of two rates, and that very rate we're actually going to decide on a particular threshold for that. But before I go into that, I'll first let's calculate the true positive rate for this. I think I just gave you that would be 95 divided by 16 plus 95. As you can see, that's going to be true positive rate. What do we mean by that here? What proportion of the crab with satellite were correctly classified? Okay, were correctly, the true positive. We label 0, we label 1 as with satellite. Don't forget the response variable is binary. So we label 1 when satellite is present, 0 when it is not. So here now is going to be 95. True and 1, true. At the predator side, 1. At the actual side, that gives you 95. That's an agreement, right? 95 divided by all the positive. So that's why you see that. Then the first positive rate, that will be 35 divided by what you see, the one without satellite. You take a look at that now. Okay. Now, there's something, what I told you the other time, that we call the AUC ROC. The AUC ROC is a very reliable way of actually distinguish, discriminate into classes. It is a plot of the true positive rate, to the false positive rate. So when I plot in the y-axis the true positive rate against the false positive rate, I did that at different threshold. Let me tell you this. When AUC equal to 0, what does that mean? Oh my God, if AUC equal to 0, that is bad. It means everything that is going to predict is going to be in error. When AUC equal to 0, what it means is that everyone in the positive class will be classified as negative class. Everyone in the negative class will be classified as positive class. That is when AUC equal to 0. Now, when AUC equal to 1, that's another extreme. AUC equal to 1 is a perfect classification where the module correctly classify all positive class and all negative class. But that is not realistic. What about AUC equal to 0.5? AUC equal to 0.5 is too dicey. It means the probability of misclassification is the same thing as the probability of correct classification. That is too dicey. In that situation, you may not be able to distinguish between noise and signal. But then which one do we want? We actually want this threshold. We want an AUC value. We want an AUC value that will be greater than 0.5 but less than 1. Okay? And that was why when you take a look at this the other time, you see the code, table predict the satellite say greater than 0.5. Okay? Greater than 0.5. So like I said, the AUC is what we normally use, which is the plot of the true positive rate to the false positive rate. We are plotting the two at different threshold value. The threshold value that range from 0 to 1. I just demonstrate to you now. The reasonable one is the one that is greater than 0.5 or less than 1, where it will classify more of in the positive class to be positive and more in the negative class to be negative. That's exactly what we want. Now, I want to go into another subtopic in the next 10 minutes. This is what we're going to be doing. Oh my God, I know that uh oh, somebody said in the chat, do we need to change the location of TPTN since the true and false exchange? Anyway, you know, it depends. Like if you take a look at you know, at times, you know, you may have it depending on the source you are reading from. But this is what I wanted to know. When we call something true positive and true negative, that's a correct decision. That is an agreement between your model and reality. That's what we mean by true positive, true negative. It now depends on what you code as 0 and what you code as 1. But we're trying to say true positive, true negative is 0 agree with 0, 1 agree with 1. But for false positive and false negative, that is what you're going to have at the point of intersection between you know, the 0 and 1, whichever way you actually see that. Okay, now what if in a situation where Predictor is categorical as well? You know, the response is categorical. Predictor is also categorical. That will now become analysis of categorical variable. Now, I want you to take a look at this example, admittance into graduate school. It's either you are admitted or not, subject to some variables. One of the variables is also categorical. And which of the variable is categorical? The rank of your undergraduate school. They put that into consideration. You know, the rank of the undergraduate school go from highest prestige to lowest prestige, from 1 to 4. Okay. Now, if you take a look at this data set here, for, you know, for 2017, this star 4051, because we follow our students after graduation. We want to see that they're really doing well. You know what I mean? So now take a look at the data now. Admit, GRE, GPA, and rank, right? You have 3 independent variable. One of them is categorical, and the one that's categorical is also rank. Now we can generate a table. Take a look at that very table now. 28 applicants from undergraduate school, okay, with a low prestige was, you know, was not actually admitted. If you take a look at, you know, admit 0, 1, okay, admit 0, 1, probably we're coding yes as 1, okay, and 0 as no. If you take a look at what I have now, if you take a look at that 2 by 4, we're trying to give the proportion of those, or the number of those from undergraduate school that were ranked 1 to 4, okay, those who were given admission and those who were not given admission. Now, if I run a module now, module 1, admit on GRE, GPA, and the rank, this is what I got. This is the result. What is it telling me? It's telling me all the independent variables are significant. The GRE significant, the GPA, even the rank is significant. Of course, you know why you have rank 2, 3, and 4. Rank 1 is actually a reference. It's in the intercept. I think you know that, right? Okay, now, do you know I can actually conduct an ANOVA, you know, nested ANOVA test between 2 modules, okay? A module, the module 0, of course, you know, module 0 is actually talking about the intercept. The module 0 is saying, okay, admission into graduate school does not depend on anything. That is an intercept module. And module 2 is trying to say, oh, admission into graduate school depend on your GRE, GPA, and rank. Look at the p-value here. Very, very small, right? It means you're actually going to reject a simple model, which means, of course, the explanatory variables here actually play a role in securing admission into graduate school. That's what I mean. Now you can interpret parameters. Let me tell you, I told you the other time, when you have a logistic regression model, they estimate that came from the logistic regression model, they are on the log scale. Look at the interpretation. If I want to interpret for GRE now, what is the estimate? 0.002264. How do I interpret that? I'm actually going to say the log odd of being accepted versus not accepted increases by that. You have to mention the log odd anytime you are interpreting that. But if you want to interpret the odd, you need to first take the exponentiation before you interpret the odd. Please take note of this interpretation. The same thing go with GRE, with GPA. But how do you interpret a categorical predictor variable, like rank in this case? Okay, now I want to go back to the result. Take a look at this. If I want to interpret the estimate for rank 2, I will do that relatively to rank 1. Don't forget the rank 1 was actually what? Reference. If I want to interpret estimate for rank 3, I will compare that relatively to rank 1. If I want to interpret the one for rank 4, I will do that relatively to rank 1. The rank 1 was actually reference. Now, and that was why my interpretation is actually, I said the indicator variable for rank have different interpretation. Having attended an undergraduate school with a rank of 2 versus an institution with a rank of 1. See, what do you think I want to interpret? When I mention that, I actually want to interpret the estimate for rank 2. If I want to do the one for rank 3, I will have to say relative to rank 1. If I want to do the one for rank 4, relative to rank 1, whatever rank I'm actually going to interpret here is going to be relative to the rank that is not showing, the one that is nested in the intercept. So take a look at that here. I said with a rank of 1 decreases the log odd of admission by that. What was that? Why do I say decreasing? Because the estimate of the rank 2 is negative 0.675. That decreases log odd. If you write decreases number of admission, you are wrong. What does it decrease? The log odd of admission. Does that make sense now? Please pay attention to that. Now, when you say that, given that all other variables in the module are at constant, you also need to mention that, because it is not only rank 2 and rank 1 that you have in the module. You have other rank. Then you have to mention that you have add other one at constant. Holding them at constant means you are adjusting them. You are accounting for them. So take notes of all of that. Okay. I don't want to rush you. Let me see. I'm stopping at slide 19. I'm going to start from this slide 19 on Wednesday. Like I said, we're finishing logistic regression this week. Any question? Before I go, I'm going to say this again. I extended the deadline of submission of the current assignment by 24 hours. There's a reason for that. Just to give you an information about the assignment. When the what is it called? In the current assignment, you have a degree of freedom equal to 0 in one of the questions. When the degree of freedom equal to 0, it means you cannot actually figure out the p-value. In a situation where the degree of freedom equal to 0 and you are comparing simple module with a complicated module, go with complicated module. I'm going to say this again. When you are comparing two modules, I'm saying that for the last time. When you are comparing two modules, because I know in one of the problems in the assignment, the degree of freedom will be equal to 0. When the degree of freedom equal to 0, there's no way the p-value will be given, right? Now, what I'm telling you now, when you are comparing simple module with a complicated module, where the degree of freedom equal to 0, go with the complicated module. Conclude in favor of the complicated module, the module in the alternative. Okay, ensure you stay safe and have a lovely day. Bye for now, everyone.